Okay, good afternoon and good morning, Marco. So, welcome to the online webinar series conducted by Applied Photonics Initiatives of ISC Bangalore. So, this is what we plan here. This will be like a one-year round webinar or seminar, depending upon how fast we can flatten the curve. That's one of the issues. So, it will be a webinar round or a seminar series on photonics and metasurfaces. So, and today we have Dr. Marco Piccardo briefly about the speaker. So, Marco is a researcher and team leader at the Istituto Italiano di Tecnologia in Milan. That is IIT Milan, right, Marco? So it's IIT. Yeah. It's also called IIT Milan. Yeah. He studies metasurface enhanced active photonic sources. So he's also an associate researcher at Harvard University where he also did his postdoctoral studies in the group of Federico Capasso. So we don't need to say much about Federico here because he's more well known for quantum cascade lasers and very recently on metasurfaces. And so he explored semiconductor laser frequency combs. He obtained his PhD in physics from École Polytechnique, working on the fundamental electronic processes responsible for the efficiency drop of the blue light emitting diodes at high current operation, for example, such as Anderson localization and Auger recombination. So actually where I met Marco there, where he was doing his PhD just 1 year after he finished his PhD after I left there. So he also received his BSc in physics from Università degli Studi di Torino. Marco, tell me if the pronunciation is wrong. Huh? And the MSc in physics from INS Paris Technique, both. So he's the recipient of the Young Award, G.F. Bassani, 2016 from the Italian Physical Society, and laureate of the PhD Award, the Innovative Materials and Applications of the Université Paris-Saclay. Since 2019, he is also the event chair of the Integrated Photonics Group of the Optical Society of America, and he also holds 4 patent applications in photonics and numerous papers, mostly published, as far as I know, in Nature and Science and high impact journals, which are very good works. Actually, would like to now hear from Marco for this 1 year, for this 1 hour, on the topic of today's talk is integrated optics solutions for molding lights in space and time. Over to you, Marco. Thanks for coming.
Thank you very much, Tapa. Okay, I'm gonna share my presentation. Okay. Laser pointer. Okay, we should be all set. Let me know if you're not seeing the presentation. Okay, thank you very much. Yes, in this webinar, I'd like to give an overview of different possible approaches to structure light often spatial in the temporal domain. So will be an overview of a few different works. We'll not go too much in depth into each of them, but just to try to give you a sense of what are different possible approaches. Let me start just by thanking Professor Dasgupta. Actually, we go back in time quite a lot. We met in 20 when we were doing our PhD together here as eating chocolate at École Polytechnique from those times. And he's always been a nice friend and colleague during these years. So I'm really glad and thankful for this invitation. Let me start just saying a little bit where the research I'm going to present was developed. As shown in the introduction, I carried out my postdoc in the group of Federico Capasso at Harvard University, where I spent 3.5 years. And there I concentrated mainly on the optical frequency comms. In particular, I realized with quantum lasers, but in general, semiconductor lasers. And so I worked a lot with the temporal and the frequency domain for creating interesting patterns of light. More recently, about 1 year ago, one member also of the Capasso group, in the meantime became an independent scientist, got an ERC grant, consolidator grant, to move to Italy and start a new lab. And he offered me a position of a researcher to lead a small team within his group. And so now we are both together at the Italian Institute of Technology, which is a network of laboratories connected and collaborating among them. And one in Milan in particular where I work is mainly concentrated on innovation and photonics. And so with Antonio, we were trying to develop new forms of light that can be useful, often based on metal surfaces, but not only. That can be useful for a number of applications, but one application that we're particularly interested in is for microscopy. And in particular, my effort within this group is to combine metal surfaces with lasers. Okay, so given the kind of different field I've been working on in the last few years, recently I've tried to combine them and into a bigger picture. So recently I've started coordinating a roadmap together with a colleague, Belgian colleague, Professor Guinness, on multimode light shaping. And the general concept is illustrated here. So often people have, traditionally people started thinking about structural light as creating patterns of light in space. So at a certain plane or propagation plane, you create a certain pattern of light. And this was the initial concept of structural light. But then this concept started evolving. And I think we can see it now as a more general concept where the new paradigm here try to be connected under the word of multimode light shaping, where actually one can consider all modes of light to shape the electric field, the electromagnetic field. And so here you consider, okay, if I have a certain frequency but many wave vectors, I can make a structure in space. And then instead, if I have a certain wave vector, let's say, for instance, a Gaussian mode, but many frequencies, I can make a pattern in time. And then I can also have combination of two, right? I can have some wave vectors and different and make space-time beams. And then, of course, I can also play not only with amplitude and phase of light, but also with polarization. So I can actually use all modes of light to create interesting patterns that can be useful for actually any application in optics. So yeah, the talk I'm giving today tries to give an overview of a few different approaches. Particularly, I'm interested in integrated solutions that can be used to shape light. So let me start a little bit from kind of the basics and what does it mean to mold light, to shape it. You can think of it, well, it depends on the domain you're working with, if it's in the space or time domain. But let's consider, for instance, a plane wave that comes onto a spatial modulator. For instance, at the moment, you can think of it just as a black box. And sort of, it's like having a canvas, if you want, on which you are creating a pattern, right? So you can form a certain shape, and these are you molded your light after passing through this black box. But still, if you look at its intensity as a function of time, nothing would be changed, right? It would still be sort of a continuous way, but now with this particular spatial pattern. Or you can think of saying, okay, I still have a plane wave, but I send it through this to a temporal modulator. You can think of it, right, like modulating the input light, and now you will have still this in a plane of propagation, still a uniform intensity. But if you monitor this as a function of time with a photodetector, you will see that this light is modulated. So this is the essence. You can the idea of shaping light is that you can create patterns in space or in time, and these are useful for a large number of applications. Like, for instance, if you want to create some landscape of light to optically trap some particles, like, for instance, with optical tweezers, but more advanced. You can use intense laser that have been typically the best one can get down to maybe 3 micron, or that's more or less the typical value. So you cannot do anything on a much smaller scale. And in time, also, you're limited by the bandwidth of your electro-optic modulator, right? So there are limitations when you want to structure light outside in free space. Now, there is an interesting alternative approach to structure light, which is doing it directly, either at the source, if you're using a laser, or in a resonator, or, for instance, even in a waveguide. Doesn't really matter. The specific box of light that you're using, the important thing is that, yeah, you're confining light, so there are specific sets of modes, and then you can work around these modes. So for instance, you can have here, I'm just sketching some basic optical modes like Laguerre-Gaussian modes or Hermite-Gaussian modes. So these are modes of a cavity or modes supported by a waveguide that you can use and combine in different ways if you have a certain ability in manipulating these different modes in order to create some interesting and more complex distributions of light. So in this way, you directly work on the modes, okay? And we can think of essentially two sets of modes. Modes that are in frequency, so you have all these modes will be, you can see them, think of them as different colors, right? Or even just spatially structured modes. So for instance, what I'm sketching here, these are higher order transfer modes. So like the fundamental would be a Gaussian, and then you would have like a different donuts of different orbital angular momentum, etc. And I'm gonna what follows, I'm gonna sort of split these two type of modes for different applications. So in particular, when you typically want to work with just time, you're mainly interested in having maybe Gaussian modes at different frequencies. And when you want instead to create a spatial distribution of light, you rather want to consider maybe in a narrow band of frequencies or even at the same frequency, just different transverse modes of your system. So let me start giving an overview of temporal patterns, how they can be created and what they can be interesting for. So as I was saying before, let's just consider all these are Gaussian modes, so spatially are all Gaussians, but they have different frequencies. So for instance, you can generate this a set of different longitudinal modes in a Fabry-Perot laser. So it's just a cavity. Maybe the simplest cavity you can think of, where light is bouncing back and forth many times and creates standing waves. And so this cavity supports a set of frequency modes, which in general, if there's no special mechanism in the laser, in general, these modes are non-equidistant in the frequency domain. So a sketch here, there's typically dispersion in these modes. If they don't talk to each other and there's just dispersion in your cavity, they're not equidistant. So what does this mean from a temporal point of view? This means that these different modes, these modes, they can be combined. In the time domain, they're going to create a pattern, which actually varies continuously in time. So keeps on evolving, and it's essentially an aperiodic pattern if all these modes are, as we say, unlocked. Now, what happens if instead there is a nonlinearity in the laser? These different modes can talk to each other and synchronize them and create an equidistant frequency comb. So a frequency comb is essentially this, a set of many frequency modes where the spacing is exactly the same in all these pairs of modes by an extreme accuracy. So when you have this in the time domain, essentially you have a periodic pattern. So as this pattern you see here will repeat itself on and on, on and on. And that's the essence of a frequency comb. Now, how can we work around the shape of this pattern? What can we do? Essentially, you can play with the phase of these different. Imagine having a spectrum of modes with a certain intensity distribution. Well, you can vary the phase. You know, in the Fourier domain, you have not only the amplitude but also a phase associated with each mode, and you can play with this phase distribution to change the pattern. For instance, I can change the phase in another way and have a different periodic pattern. Of course, I could also do this by playing with the amplitudes. So I have two nodes. Per every mode, I have two nodes that I can use to adjust my temporal pattern. So one way of reshaping a frequency comb is to use what is called 4F shaping. So you come in with a certain temporal pattern, for instance, let's say a single pulse. You send it onto a grating, so you disperse it, and then at 2F, after a lens, you do a Fourier transform. You actually enter in the Fourier domain, where all these different frequency components, you see, like for instance, the red and the blue, are spectrally separated. And there you can use a modulator array, can be realized in many different ways, but something that addresses mode by mode and adjusts its intensity in its phase. So just to after recombining again all these modes together, you change the temporal pattern, okay? So we started with a single pulse, and we came out with a set of weaker but different pulses. So this is a way to shape temporal pattern, but outside the cavity. It's not compact. Typically, you need, this for a system requires grating, lenses. So recently we tried to think if it's possible to directly at the source, and suppose you have a source that normally would generate a train of pulses, is it possible to instead create to change radically the dynamic behavior of the source? So this is work we did in collaboration with a group of Benedikt Schwarz at TU Vienna in Austria. And I like the way one can understand what's going on as an analogy. Essentially, you can think of these lasers. These are small semiconductor lasers, so chip scale. They're actually quantum dot lasers. You can think of what's happening in these lasers with an analogy, with a classical analogy, which often helps to think and understand these things, which is that of coupled metronomes. So let's see how this analysis works. You can think of as your laser producing a frequency comb, so many frequencies. These are all optical frequencies. Now the thing is that each pair of these frequencies bit together. This produces a bit note. This is similar to what happens when you have two different sounds. They can bit together and you can hear the different frequency. So this happens also in the electromagnetic regime. So these, for instance, these two optical modes can bit together and create a bit tone, which you can think of it as a metronome, okay? Oscillate the difference frequency between the two modes. And now this happens for all the pairs of modes, okay? So you have this set of metronomes, okay? Now, what is actually gonna determine the behavior of the laser, whether in particular is gonna emit pulses or something else, some different type of pattern, for instance, no pulses, really depends on how these bit nodes are synchronized together, on what's their phase relationship. So if they're all in phase, as in this case, this would correspond, you can think of it as many metronomes that are standing together on a platform that is free to move, to oscillate around. And so, you know, this experiment is very nice, this classical experiment. They're free to oscillate. And so initially they're not synchronized, they synchronize together and they end up being in phase. So this means that the platform will oscillate a lot. And this, in this analogy, corresponds to creating pulses at the output of the laser. But now you may have also seen this twist of this experiment, which is you take again the two metronomes on the platform and you put them on a liquid bath, which acts as a damping, as a loss for your system. Now, since the oscillators are smart enough, they're going to say, rather than dissipating all this energy in the bath, we're just going to synchronize the two metronomes in antiphase. So they're going to still oscillate, but there's not going to be a net displacement of the platform, okay? And this is what we observed that also happens in our laser. So if we remove this fast saturable absorber and we just leave the whole gain medium without any additional section, essentially the gain medium acts as a damping, as a source of damping, as a damping loss. And this unfavors any oscillations in the waveform. So you can radically change your output from pulses to no pulses just by removing this section. So all this is done at the source. And I showed you that you can radically change the temporal pattern of your laser. And these are like experimental results that show essentially this change in behavior. Now, speaking about temporal patterns, I'd like to move to another topic that we also investigated recently. And in here, we started thinking, okay, what should happen if instead of using a Fabry-Perot laser, still semiconductor laser with Fabry-Perot cavity as the one I just showed you, what would happen if instead of this, we start using a ring laser? Okay, and the thing is that so far, it has long been thought that if you just take a ring laser and it's unidirectional, so light only circulates in one direction, it can be clockwise or counterclockwise, there should be only a single mode oscillating in the cavity. And so it means that the intensity as a function of time should be essentially flat, because you have just the intensity of a single mode, right? The only instability that was predicted so far was essentially what's called the RNGH, after the name of this scientist, the RNGH instability, which should occur only if you pump the laser really high. So if you go 9 times above threshold, it was expected that eventually you would the single mode would start developing sidebands and so create a frequency cone, and eventually a temporal pattern should occur. But the thing is that in many ring laser, it's really impractical to get to 9 times above threshold. Just the heat that you create in pumping so hard the laser, it just burns the laser. We actually fabricated this device mostly as a control device. We were having other ideas on how to induce pattern in these cavities by adding some defects here and there. So actually transforming the ring laser. Yeah, we just said, okay, it's always good to have a control device to just verify that in our laser everything happens behaves as expected. And what we measure with this was a great surprise. So at this moment we switched to quantum cascade laser. We can just think of them as semiconductor lasers emitting in the mid-infrared region. What we measured with our great surprise was that the pattern was not at all flat. There were some oscillations, and in particular in the frequency domain, there was not just a single mode but many modes. And this came as a really something completely unexpected that got us thinking for, let's say, several months, scratching our heads, trying to understand what was going on. And we ended up realizing that this phenomenon is due to an instability, which is due to a turbulent process. So you probably, turbulence is something that we experience on a daily basis. Like, for instance, if you're sipping now maybe some coffee and you put some milk in it, stirring in it, you're going to see turbulence in it, right? Or one example that I often like to mention is when you look just at flow of any liquid. It could be like, for instance, of the smoke from a candle, or just from water from tap water. You can see the transition from laminar to turbulent. So laminar, you can think of the laminar flow as essentially an approximation of single mode flow that eventually can evolve in a turbulent flow, so a multi-mode flow. So how does this happen? This typically requires some nonlinear interaction in your medium that creates an instability, a wave instability, and that leads from a laminar flow to go to the turbulent flow. And there is an analog in photonics, but so far this was for passive Kerr cavities. So these are microresonators that are completely passive devices where you input light from the outside in a bus waveguide. Part of it is coupled to the microresonator, and so it starts oscillating there. So you start again from a single mode with constant intensity, and at the output, due to this wave instability, in this case often called a modulation instability, you end up having at the output a train of solitons. There are actually multiple patterns you can have, but an interesting one is a train of solitons that corresponds in the frequency domain to a frequency cone. So you see, thanks to the nonlinearity of the medium, we started with just a single mode, the red mode here, and then this created a skirt of sidebands. And so we realized that what's happening in this ring quantum cascade is something similar that could be explained with a beautiful equation that is universal in observing many branches of physics, in hydrodynamics, in Bose-Einstein condensates. And I really like it because it's particularly simple, as a simple form, but it's powerful, and it has powerful implications. So what you see here, A, is just the amplitude of the field. This is the time derivative, this is the spatial derivative. And apart from that, there are just 2 parameters, alpha and beta, that have a different physical meaning depending on the system you consider. And you can consider this system parameter space denoted by where the 2 axes are alpha and beta, the 2 parameters of this equation. And this equation has been long studied. You can separate the parameter space in 2 types of regions, a stable region and 2 unstable. So let's see what happens if our system At the moment, it could be our laser, but it could be also another system that obeys this equation. Let's see what happens if our system has these parameters such to lie at this point in parameter space. So you see that even if you start initially, you can think of this x as a coordinate along our ring, for instance, and this t as time, so the temporal evolution. You can start from a certain noise, some noise fluctuation in the spatial coordinate, and just let evolve and see what's happening in your system as a function of time. So that's how you should read these plots. This is, again, unwrapped coordinate of our ring, and then on the vertical axis you see the time evolution, what's happening in this in the system. And you see that if the parameter space of our system lies in the stable region, you will see that it just even though there's noise initially, in the end you have a uniform intensity, right? The field which is sketched here is uniform because you're in the stable region of this equation. Now, if instead you place a point here, which is kind of far from this boundary, which is called the Benjamin Fair line, you end up in a region of amplitude turbulence, which is very fascinating. So you start again from noise, but now the noise builds up, and you end up having very strong amplitude fluctuations. This is called amplitude turbulence. And now, if you're very close or rather close to this boundary region, you start again from noise, and what you end up having is phase turbulence. So in this case, the amplitude is not oscillating a lot; it's almost constant, but mainly the turbulence is in the phase, in the couple, in the phase of your electric field. And so what we realized here, I'm kind of cutting it short, but just realize that our ring laser actually obey this type of physics, and they essentially the surprising instability that we observe in our ring lasers is due to this sort of physics. So we start again in our ring laser with initially just some noise, and you see that due to the phase turbulent instability, you start having multiple oscillations inside the cavity, which energies of the laser can end up talking to each other and lock together. You can really think of it as the morphogenesis of a spatio-temporal pattern, and then these different features starts locking together, and eventually there's something that is periodic, right? So from round trip to round trip, this pattern repeats itself, and this is when we're in the frequency convergence. So this was quite surprising, quite interesting. And we started seeing in this sort of a connection between passive and active devices. So as I mentioned before, these wave instabilities were known in Kerr microresonators, which are just passive devices. And we started thinking, okay, there seemed to be really a deep link between these two. We saw similar instability. So about a year ago, I asked Professor Luggiato, who is known, among other things, to have developed an equation which is called the Luggiato-Lefebvre equation that later on was discovered to apply very well to the case of Kerr microresonator, and today is routinely used to describe their physics. And I asked him, since we feel that we have this deep analogy between the two systems, would it be possible by any chance to develop a sort of Luggiato-Lefebvre equation but for active cavities, so for lasers? And with some work and thanks to all the collaboration in his team, we ended up developing a new equation, which we call it a generalized LLE, generalized Luggiato-Lefebvre equation, that now can comprise all these systems. So it's a single equation that can describe you all these different systems. So both passive and active devices. And inspired by this generalization, we started thinking, well, maybe there's something we can combine here between the Kerr microresonators and free-running ring quantum cascade lasers. Because if you see here, there's just a cavity that is purely passive and it's pumped from the outside. So there is an injection port, and then here there's no active medium. Well, in our lasers, we have just an active medium. So what happens if we add in our lasers an injection port, like in this case? So what if we try to study an injected ring quantum cascade lasers? And the results for the moment are just theoretical. They were reported in this recent paper, but they're very encouraging. They show that we can see average patterns in injector. So this external knob allows us to see much more temporal patterns in this system directly at the source. So just by varying the frequency and amplitude of this injection seed inside our ink lasers, we can vary from Turing patterns, which are these spatially extended oscillatory patterns that extend across all the cavity. We could vary these from these to temporal solitons. So these are localized structures in the cavity that corresponds to narrow intense peak that are very interesting for many applications. And here is shown just by varying tweaking some of the patterns inside the cavity, you can see how much the temporal pattern can be shaped. And all these at the source, which is very interesting, in particular for quantum cascade lasers. They cover the mid-infrared region of the spectrum, which is very strategic for many applications, such as, for instance, spectroscopy. Another cool thing that could be done, for the moment still just theoretically, but is to write solitons in the cavity. So you can send a set of pulses in your cavity, and they, for instance, here you see we start sending a soliton, just a pulse from the bus waveguide, and then this starts circulating in the waveguide, and then you can write a sequence of them, and they will keep on circulating in the waveguide, so they will stay there. So you can think of this as encoding information in your cavity just from the outside. So it's writing really a pattern, which has a different spectrum depending on the number of solitons you inject. So also this is quite an interesting potential. Okay, now I'm gonna switch gears a little bit from the temporal patterns to spatial patterns with an approach that was initiated by my colleague Professor Guinness in Belgium. And the idea here is to exploit multiple transverse modes in waveguides. Again, here, going back to the diagram I was showing before, let's forget now about the multiple frequency and the multiple Gaussians. We just concentrate on a set of frequency, and we consider not only the Gaussian mode, the fundamental mode of a waveguide, but all the higher order transverse modes. Okay. Of course, the fundamental you have to know is that in a waveguide you can support typically multiple transverse modes if the waveguide is wide enough. So, for instance, you can have the fundamental mode here, second order, third order, and so on and so forth. And you can obtain them just by solving the dispersion relation of your waveguide. So now, where the idea comes in. The idea is the following. What if we add in our waveguide some mode converters? So we come in, for instance, with a Gaussian. So initially we inject a Gaussian in our waveguide, and we use these mode converters to change the mode, to go from, it's a sort of a special mirror that reflects back the light, but by changing its spatial modes. Okay, so typically this can be realized with a grating with a specific periodicity. And the shape it depends on exactly the kind of efficiency you're looking for. And okay, so this is the first element. So we use a multi-mode waveguide with mode converters. Okay, but now how can we obtain a desired combination of modes, of different transverse modes, so that when you sum them up, you make them interfere, you obtain a pattern, a spatial pattern that you want. And so here is the key idea. The idea is to do cascaded mode conversion. So you inject light of a given mode. For instance, here is beta 3 is the third order mode. It could be another one, but it's just an example. So you inject a specific mode in your waveguide. Now it enters the waveguide, and eventually it's going to enter this area between two mode converters. And the essence of the idea is that you want to do many bounces, multiple bounces between these two mode converters. And at every bounce, you want to change the mode that is propagating in your waveguide. So let's look at an example because it's easier to understand than just a number of words. So here we come into this waveguide. It's always the same, and just showing here multiple at multiple successive times. So I come here with the third order modes. And first of all, I see this converter. It converts 1 into 2. Now, the thing is that this corresponds to a specific wave vector in reciprocal space that has a specific length. It would connect 1 to 2. So 1 actually to -2. And if you apply this wave vector to mode 3, nothing happens. So essentially, let me go back one slide. If you send this mode 3 specific mode converter, nothing happens. It just goes through. That's the beauty of the idea. The mode just goes through. So it goes through, it just essentially doesn't see this first converter. So we are now with the mode here. And now this mode is going to see another converter, now converted 3 to 2. And now this mode converter has the right periodicity to connect mode 3 to -2. So essentially you are reflecting, bouncing off, the mode is bouncing off and giving back a second order mode that is propagating back. And now the second order mode comes here and it's gonna see the mode converter 1 to 2. And so it bounces back again. So we made 2 bounces and we created at the end in this central area between the 2 mode converters, we call this area the arena. In this arena, we created 3 different modes, so a superposition of modes that we completely selected. It could be others. Everything depends on the mode converters. And we can even tailor the phase and amplitude of these different modes in order to create a superposition of modes. That on top of the waveguide, now you have a near field landscape. So in the near field, you have a pattern of light that was designed essentially arbitrarily. And this just to say that even though I showed you a very simple example, all this can be nicely generalized to, for instance, even if you just use 3 mode converters, you can end up exciting 6 different modes inside your arena. And this can be done really for any number of modes, at least theoretically. So it's very general. And of course, the more modes you use, the finer are the features you can design. And these are just a set of examples of different landscape we created using this theory. So for instance, we could make a sigmoid, or you can make a Gaussian, you can make a slope. All this is happening right on top of the waveguide in the arena between the 2 mode converters. And then just for fun, since there was this famous quote from von Neumann, which maybe you've heard, which says, with 4 parameters, I can fit an elephant, and with 5, I can make him wiggle his trunk. Well, with 4 parameters, so with 4 trunkless mode, we show that we can essentially fit the shape of an elephant, just to show how arbitrary these landscape are. So what I showed you so far was just theory. We worked on a first experimental proof of concept, and to make things easier, at first we started with a microwave waveguide. So it's all by Maxwell scaling laws. Essentially, it would be the same in the optical domain, but we did a microwave first. And so this is a multi-mode microstrip that supports multiple modes. And there was some microwave engineering in order, for instance, these input tapers that you see here allows to inject a specific mode at the input, which is the mode that we wanted. And then there is these are the 2 mode converters, what you see here. This is the arena, the central part where light is structured. And these are output tapers that just ensure that anything that goes through is completely absorbed. And then, okay, you can feed these microstrips with a specific frequency, the frequency the cavity was designed for, not the cavity, but the waveguide was designed for. And then it's a matter of revealing these features. And so we did this by using a near field probe. It's sort of like an Elson measurement for those who knows near field optical microscopy. But this is done still with an antenna in the near field, but at microwave frequencies. And we could show that this the landscape we create is as the theoretical one. And so we're still working on this, of course, on the most exciting developments of this. And now we're heading towards optical devices. So these are all integrated devices that can create landscape on top of the device. Now I'm getting to the last small section of this, and I'm going also to metasurfaces, which is a bit the sort of connecting line of this series of talks, as far as I could understand. So this work done with Antonio Ambrosio at the Italian Institute of Technology. And here we're interested in particular on generating optical vortices for a number of applications. So optical vortices, you know, they are like light beams that carry orbital angular momentum. And they can be pictured in essentially as they propagate, they have this sort of a corkscrew profile. And they can be pictured in amplitude and phase, just as a donut in amplitude, with particularly a vortex core at the center, so no light at the center, and an azimuthal phase modulation. So for instance, this would be, you see these 5 sectors in phase would correspond to an orbital angular momentum charge of 5. So they can actually rotate matter, induce transfer angular momentum to matter. And there has been a number of ways to generate these type of optical beams in the last few decades. Everything started from holograms, then people started doing this with just transformation based on cylindrical lenses, and so on and so forth. And more recently, people started switching to metasurfaces, which give a great control over the amplitude, phase, and polarization of your beam. So the traditional approaches so far to generate these type of vortices were based on Q plates and J plates. They're called like this. Q plates essentially are based on the geometric or Pancharakhnon-Berry phase. So the phase profile that you give impart to light is essentially given by a rotation of pillars. So these are all identical pillars. Each of them acts as a halfway plate, but their rotation, their local rotation, can give a different phase, a conversion of polarization from right circular polarization to left circular polarization, and as well give a global phase, a local phase. So using this, you can create optical vortices of a charge that you want. And then another approach was developed more recently. It's based on J plates, which allow you to control simultaneously the total angular momentum, so both the spin and the orbital angular momentum of light. And in this case, you see the pillars are not all the same across your metasurface. They can have different sizes. And now what is exploited in this case is the propagation phase, and in particular the birefringence of the nanopillars. So the thing is that when you use Q plates or J plates, the control is purely on the phase. So you create a certain phase pattern. So going back here, you just create a phase pattern, but there's no amplitude control to generate your beam. So what you end up having, since you're not creating eigenmodes of free space, you're creating multiple P modes, multiple radial modes at the output of these plates. So for instance, here we start with the RCP light, we come out with LCP lights, and there are many OAM modes, but all with different P. So in the far fields, whether you're generating the vortex with this or this approach, you end up having a donut with many rings around, okay? This often is unwanted because makes your beam not pure, your vortex not pure. And so what we develop more recently, and all this is what is really due to is to the fact that your LG mode is in principle should have not only a phase term but also an amplitude term. But again, with these two metasurface approaches, we are just controlling this phase term. And so the lack of these amplitude terms in the far field creates a multitude of P modes. Now with the new type of plates that we designed here, which we call the P plate, because it allows to control the P or radial mode, we can at the same time control both the phase and amplitude of the outcoming beam. So how does this work? This essentially means doing complex amplitude modulation with a single metasurface. And you can think of it in the following way. When you have a nanopillar, you have multiple degrees of freedom, which are the two sizes of your rectangles and the orientation angle of the nanopillar. And you know the birefringent element can be described with a geometrics, where these two, the two sizes of the pillar end up defining the birefringence, so the polarization property of your nanopillar, and a global phase that is transmitted through the nanopillar. And if you combine, so the idea is to exploit these 3 degrees of freedom to control both amplitude and phase. And so with one of the 2 sizes, you can set a global phase, which we're going to use eventually to take into account of this term, the global phase term. And then we combine the other 2 remaining degrees of freedom, so the rotation angle and the birefringence, in order to do a polarization conversion. So we convert, for instance, what we did here was to generalize this for any input polarization. So we can come in with a certain elliptical polarization, convert it into another elliptical polarization, such that after projection through a linear polarizer, we have just linearly polarized light with an amplitude that is as desired. Okay, so this shows just by using these 2 parameters, alpha and delta phi, so the angle and the birefringence of your nanopillar, you can actually modulate the transmitted amplitude after the polarizer as you want, from 0 to 1, so you have a full dynamic range. It is just to show that by combining these different degrees of freedom, we can have, rather than the usual far field that corresponds to a donut with many rings around, so an impure vortex, we can actually have in the far field a pure vortex. And this can be designed for any input polarization, not only for horizontal polarization, but also for elliptical polarization. And if you want, you can even just design any radial mode that you want. So for instance, here, we did it for a higher order P mode. So the charge is just 1, as you see here, but the order of the radial mode is 3. So you have full control over the amplitude and phase of your output beam. And so now what do we want to do with these metasurfaces? We want to combine them with lasers. And I'm just going to say a few words of this ongoing work. So the difference with respect to the semiconductor laser I showed you before, that typically are designed for single mode operation and that they are characterized by a small Fresnel number. The idea here is that to use large lasers, there are multi-modes. So they have a large cross-section, they have a large Fresnel number, and typically they support many transverse modes. So what you see here is, for instance, in the Laguerre-Gauss basis, there are many modes supported. And the whole idea is, can we sort of pick the superposition of modes we want here, similar to what was done before with waveguides in the near field, but can we pick the superposition of modes that we want to create a profile, a pattern that we like? And this was done before in the past, particularly in the 80s, in the 90s. People studied from these large multi-mode solid-state lasers the spontaneous generation of spatial patterns. And there are a variety of fascinating phenomena that can be observed. For instance, these interacting solitons. So solitons really come close to each other, and due to nonlinearities, they can just avoid themselves. You can have these sort of soliton molecules, hexagonal patterns, spontaneous vortices, etc., etc. But all these patterns are spontaneous, so they're really hard to control, and it's more like the physics of the laser that determines what's gonna come out. And now the direction in which we're working on is to introduce the metasurface inside the laser cavity where there's a gain medium and sort of favor a specific type of pattern to be generated directly at the source, which has a lot of interest because you can end up having powerful output beam with controlled spatial shape. And a part of this was already done very recently by adding a metasurface in a second harmonic cavity. So here there's not gain, but it did show that one can generate rather, as opposed to the external case where one has a donut with many rings around, just a single ring. But now we are going in the direction of combining this with a gain medium and working directly at the source. So with this, I'm done with the talk. This is just a final slide showing the key people involved in the work I presented. And I thank you for your attention, and I'm available for any question.
Thank you, Marco. So the floor is open for the question now. So if anybody has questions. Just one question, Marco. So did you try to do some experimental, already you tried some experimental verification on this, the last?
On which step, sorry?
It is the last part on the using the meta surfaces for the vortex generation. So this you have already tried using this in the second harmonic cavity, right? You tried to do already the experiments.
You're saying in the laser or outside the laser?
Yeah, in the laser. Yeah.
This is ongoing. Yes. So it's we are having the first results now. The activity started only recently, they are giving a control over the output pattern. One difficulty we are having at the moment is that, of course, when you put a metasurface inside the cavity, the power density is typically very high, much higher than the cavity, and so it's if you're not very careful with the operation of your laser, there is a risk of damaging the metasurface just because of the
right. Yeah. So, but I mean, so when you talk about just asking from the, I mean, it's out of the context here. Just curious to know that. So that means if you kind of use it above the absorption so that it doesn't heat up the metasurface, right? If the laser, should it work or?
If I just cool down the metasurface.
Yeah, somehow, or you shine the laser light so that it is above the absorption band of the material that you use.
Well, we are using dielectric material, but there's also silicon for the pillars, which has a small amount of absorption. Of course, the farther you are from absorption, the better this gets. Absolutely. We're also thinking that maybe just having a sort of encapsulation of the nanopillars with a dielectric could help. So if one could make like just a metasurface with nanopillars, but then encapsulate them around with a dielectric, this would allow that even if the silicon sort of tends to melt, it's still sort of held together by the.
I mean, the structure remains more or less same, right? I mean, even if the silicon melts, right, the polymer outside will hold the structure. That's what I mean, right?
But more than a polymer, I was thinking really something like maybe even a silica skeleton.
Right. It's organic material on top. I mean.
Yeah. But actually, whatever can sustain it. There may be just other options to just completely make these out of silica rather than using silicon. We're at the first, but it's not terrible. Let's say it just limits how much you can push the current on your laser. At some point, it just gets too hot. But I guess it's a common problem. Okay. I see there is another question.
And Deepak, please go ahead. Hello. I see a hand up, Deepak Kumar. So he was muted.
Able to unmute himself.
I think he's muted, right?
Hello.
Yes. Yeah, sure. Go ahead.
Yeah, nice talk, Marco. This is really exciting. So I have wondering, like you talk of circular resonator, then you allow the laser, and you are calling it like circular laser trajectory, right? So basically, I'm curious, like why you choose for the like circular geometry. So can we think for some other geometrical aspects as well?
Yes, so it's true. So that doesn't have to be necessarily a circle in say a ring. It could be also, for instance, a racetrack, or more like if you want a stadium shape. But what we were really interested in this case was to have, if you want, periodic boundary conditions. So it's like having a Fabry-Perot, but then closing it onto itself. And there is a fundamental reason for this, is because we want to allow to have a unidirectional regime. So the light only circulates in one direction. That's really what we wanted. Because if you have like a Fabry-Perot, just a laser bar, let's say, then light is going to bounce back and forth And this creates it's called the spatial burning, the phenomenon. It creates a grating in the intensity, but also a grating in the population inversion. And this changes completely the physics. You don't have anymore this phase turbulence that I mentioned before. So to observe all this interesting physics of solitons, phase turbulence, you need really unidirectional operation, and this you can only do it with whatever shape, but it has to be closed onto itself. So not necessarily a ring, it could be a stadium. Maybe there are more interesting shapes than a ring, but it has to be closed.
Mm-hmm. And my next query is like, what are the current opportunities that the field of meta surface is providing? So like, what are the next challenges in the field?
Well, I would say this really depends on the application you're looking for. For instance, I come from the group of Federico, where Capasso, where most of the interest was in doing lenses, so meta lenses, very flat lenses. And there, the challenge, I would say, the key challenger is for a long time been creating achromatic metasurface, so meta lenses that respond in the same way to different frequencies. So that if you want to focus light from all the visible spectrum to a tight spot without chromatic aberration, you need to solve this problem. And the same, combine this with a large numerical aperture. So the dream there is a very large metasurface that at the same time is achromatic. That's important. That's one important challenge, and then another important direction which many people are working on is having tunable metasurfaces. So this would be very nice, right? Imaging a distribution of nanopillars that then you can sort of the phase profile that this imparts, you can tune it. Just maybe, I don't know, it could be like a mechanical stretch, so you could just with a tensile strength kind of change the size of the metasurface, so maybe change the focal distance of your lens, or just completely change the phase profile is imparting. So on this there are many different initiatives coming in. Some people are working more on nonlinear approaches, so maybe using pulses to change what the metasurface is doing, some sort of short transients. There's a number of different approaches, but I would say tunability and having high performances in terms of achromaticity and large numerical apertures are the key challenges.
And you talk about somewhere in the middle about the implementation of the dielectric metasurfaces. So what I understand, it is regarding the reducing the losses in the system. So I can see recently this superconducting metasurface are also coming towards reduction of the losses. So anything you can comment regarding the dielectric and the superconducting in comparison?
Not really, unfortunately. I'm sorry. I haven't really looked into these superconducting metasurfaces you are mentioning, so I wouldn't be able to do a comparison. I've only worked with the dielectric metasurfaces.
Okay, nice. Thank you very much, Marco. Yeah.
Thank you.
Thank you. Any more questions, queries? Okay. If not, let's thanks Marco for the time. And thank you, Marco, for giving a nice talk here.
Thank you very much.
Yeah, we'll see in the next month, maybe with another person, and we'll keep posted in the channel. So till then, have a good day. Thanks, Marco. Bye.
Bye-bye.
Bye.